Hello everyone, my name is Chukwemeka Okeke, aka Lewis, and I'm from Liberty University. I'm here to talk about energy from fusion. This is actually an operational speech for tokamak modeling. For those of us wondering what a tokamak is a machine designed to produce energy through controlled nuclear fusion. It uses powerful magnetic field to confine a hot electrical charged gas called the plasma in a donut-shaped chamber known as a torus. And of course, we can't talk about tokamak without talking about nuclear fusion. So what is a nuclear fusion? A nuclear fusion is a reaction that happens when two nuclei come together to become a nucleus. When this happens, it expels energy. This energy could be used as electricity. Before we continue into the scope and purpose, I want to talk about three very important aspects of the tokamak. The first is the magnetic confinement. So the magnetic core generates toroidal and palladial field that twists around the plasma, keeping it stable and away from the vessel wall. Another very important aspect of the tokamak is the plasma heating. The plasma must reach a temperature of over 150 million Celsius, which is actually hotter than the core of the sun, to enable fusion reaction. And the third aspect is the fusion reaction. So what happens in the fusion reaction? Light atomic nuclei like hydrogen and isotope collide and fuse, releasing massive amounts of energy. Now you get it. That's where electricity comes in. The purpose I'm modeling a tokamak and the scope I'm willing to cover is first, simulating and validating future energy system using multi-scale modeling. Now the goal here is to talk about the improved predictive reliability in the fusion system. The second purpose and scope I'm willing to cover is to focus on plasma temperature profile under heating condition. Now the goal here is to highlight plasma behavior, especially temperature profile, as a key operational metrics. The last but not the least is very, very important to me. I want to support global mission for sustainable fusion energy. One of the key ingredients in nuclear fusion is the plasma. Now, I want you guys to think of plasma as a fluid with chaotic behavior, like boiling water, but at million of degrees, very, very hot. Speaking of the improved predictive reliability in fusion system, the multi-scale fusion modeling is used to simulate a tokamak. Now, the multi-scale fusion workflow is designed to integrate models that operate at vastly different scales, both in space and time. It uses temporal coupling, which links fast-evolving phenomena like plasma instabilities with slower processes like thermal transport or structural evolution, which happens in seconds to hours. Now, the previous one happens in milliseconds, which is very, very fast. The second way it does this is by spatial coupling, which bridges core plasma simulations, millimeter scales, with edge and divertor regions, which are in centimeter to meter scales. And even reactor-wise system like cooling loops and magnetic cores uses achieve true modular interface and standardized data exchange protocols, often using tools like Model 3 from the VMCA tooling kit. The result of this process is a coherent simulation pipeline where each model contributes its specialized insight without losing the broader system context. Instead of using a fixed time step, the NFW uses the simulation dynamically, adjusts based on solution gradients. This means faster convergence during stable period and final resolution events. It's especially useful in fluid structure interaction and plasma edge control. On temperature controls, new control scheme allowed for the precise regulation of ion temperature profile, each in the core edge transition. This helps maintain physical realism in transport model and improve coupling accuracy across spatial domains. Together, this feature supports multi-scale fusion workflow by balancing computational cost with physical fidelity. One of the challenges we have in fusion modeling is a time scale mismatch. And why is it a problem? It's a problem because fast turbulence affects slow transport, but simulating both together is computationally intensive and can lead to inaccurate coupling if not properly synchronized. So that's where MFW comes in. It enables physical accurate, computational efficient, and operational relevant fusion modeling, essential for reactor design and validation. For the uncertainty quantification during the simulation of the tokamak, the multi-scale fusion workflow MFW differentiates between epistemic and eleutheric uncertainty. The epistemic uncertainty comes from lack of knowledge and can be reduced, while the eleutheric uncertainty arises from inherent randomness and cannot. Now, the MFW exposes the behavior of the plasma using the gauging heat source and the polynomial chaos expansion. The Gaussian heat source models localized energy disposition, while the polynomial chaos expansion quantifies uncertainty by expanding model outputs in terms of random input variables. So, quick question before we continue. If you had to optimize a heating system, which parameter would you adjust first? Will you adjust the position? Would you adjust the amplitude or the weight? For me, I'd adjust the position first to target the most responsive plasma region, then fine-tune the amplitude and width to control energy delivery and spread. The MFW analyzes sensitivity of the plasma using the Sobel indices. The Sobel indices are a very powerful tool in global sensitivity analysis. They quantify how much each input parameters contribute to the variancy in a model's outputs. The first order Sobel index measures the direct effect of a single parameter. The second Sobel index captures both the direct and interaction effects. In fusion modeling, this helps us pinpoint which variable like magnetic field strength or ion temperature or confinement time most influences outcome, like the energy yield or stability. By focusing on the high impact parameters, we can optimize simulation, reduce uncertainty, and guide the experimental design more effectively. Here you can see on the screen that the Sobel analysis shows that the width has a low total order index, meaning it contributes very little to output variability. This is important to tell us that width isn't a key driver in system behavior, so we can treat it as a fixed or a simplified parameter in future models. That reduces complexity, speeds up computation, and lets us focus on parameters that truly matters, like the amplitude or the heat source location. To validate how reliable our data is from the multi-scale fusion system, we're going to be using experiment from the ASDX upgrade Tokamak. The ASDX upgrade Tokamak is a tungsten wall Tokamak designed to simulate reactor relevant conditions, especially those expected in ITER. It's a powerhouse for studying edge physics, transporting barriers, and non-inductive current drives. The diagnostics are rich with Thomson scattering, ECE, CXRX, and more. With so many data streams, we face a challenge. How do we combine them reliably? That's when our Bayesian data fusion comes in. It lets us integrate diverse measurements, each with its own uncertainty, into a single coherent estimate. Instead of relying on one diagnostic, we fuse them probabilistically, updating our belief about plasma parameters like temperature and density. This not only improves accuracy but also gives us a full uncertainty profile, critical for validation and predictive modeling. Now, the different diagnostics often measures plasma parameters like temperature or density at different spatial locations. For example, the Thomson scattering might give us an electron temperature at one set of the radar points, while the ECE provides the data on a different grid. To fuse these data sets together or compare them meaningfully, we need to interpolate. This is estimate value at common spatial points. This ensures all data align on the same grid, enabling consistent analysis, visualization, and model validation. Without interpolation, we'll be comparing apples and oranges, misaligning data, and this leads to misleading conclusion. Have you ever seen two graphs that look similar but are statistically considered different? That's what we encounter here. If you look at our screen, you'd see two different graphs containing different parameters, each comparing our simulations and the experiment from the ASDX Tokamak. Now we're going to introduce compatibility measurement. One, the W subscript TOT, and the second one, the Z test. Once we fuse data from multiple diagnostics, we need to ask how compatible are these measurements. That's where the compatibility measure W subscript TOT comes in. It quantifies how well different data sets agree. Considering their uncertainty, a low W subscript TOT means that the diagnostics are consistent, which is great. A high value suggests tensions or disagreements, which might point to semantic errors or miscalibration. To assess this statistically, we use the Z test. It compares the difference between the two measurements relative to their combined uncertainty. If the Z test scores small, the measurements are statistically compatible. If it's large, say 2 or 3, we flag it for further investigation. Together, the W subscript TOT and the Z test help us validate our fusion process and ensure our model are built on solid ground. If you look at the score of our WTOT, you can see that we have a 0.05, a 0.50, a 0.95, and of course the Z test. Now it's important to understand that low weighting on asymmetry, that's looking at the W0.05, it's a good sign. It aligns better with physical intuition because minor asymmetries in plasma profile often arise from noise or localized effects and should not dominate model validation or optimization. Looking further into the simulation, if you look at simulation A has a better agreement due to higher variance, while simulation B, though more refined, showed poor compatibility due to reduced fluctuation. This table compares how different metrics interpret same simulation data. Notice how the metrics like the Westensian and the Hellingers are highly sensitive to variance, which can exaggerate differences even when profile looks visually similar. In contrast, the compatibility measure W underscore TOT with a lower symmetry weight and the Z test focus more on mean agreements and statistical confidence, often aligning better with physical intuition. Which of these metrics do you think gives the most fair or useful comparison? In conclusion, is precision always better in simulation or can it sometimes obscure reality? For me, I'd say precision in simulation isn't always better, especially when it obscures reality. A high precise model built on flawed assumption can mislead more than inform. In complex systems like fusion reaction, it is often more valuable to prioritize operational accuracy and robustness over excessive details. The goal is not perfect numbers, but meaningful insights that guides real-world decision. Finally, fusion energy isn't just a scientific challenge, it's an operational one. Industrial engineers play a key role in bridging that gap. They optimize everything from reactor assembly lines to maintenance schedules, ensuring systems run smoothly and safely. Their expertise in process design, data analysis, and human-centered engineering helps turn complex fusion challenges or technologies into scalable, real-world energy solutions. In many ways, they're the quiet force behind making fusion practical, affordable, and sustainable. As global energy demand surges, fusion offers a scalable, sustainable solution, but its valuability hinges on how well we understand and predict plasma behavior inside reactors. That's where our modeling and validation work comes in. By refining metric and ensuring simulation matches experimental data, we're laying the groundwork for operational confidence in future fusion systems. This isn't just about physics, it's about enabling a clean energy future that's equitable, resilient, and globally scalable. Thank you very much.